All right. I'd like to see if we could clarify some of the controversy or some of the misunderstandings regarding approximating normal distributions with, or approximating binomial distributions with normal distributions. And so let's go ahead and see if we can do this with this problem. We have a random sample of size 500. So we've sampled 500. And they were selected from a binomial population. What that means is there's a set number, 500. The chances of winning are always the same, and there's only two possibilities, winning or losing on each trial. And so the probability of winning is 0.1. Okay? And we're going to approximate this using a normal distribution. So for a normal distribution, we need two statistics. We need the mean. The mean in this case is the probability of winning. So the mean is 0.1. The standard deviation in this case is the square root of the chances of winning times the chances of losing divided by n. Okay? So in this case, that is 0.1 times 0.9 divided by 500. Okay? And so that's our standard deviation. And we can come up with an approximation here. Let's go ahead and do that. What I'm going to do is I'm going to do this. I'm going to do the mean is 0.1. And I'm going to do the standard deviation with an S, square root 0.1 times 0.9 divided by 500. Okay? And 0.01342. 0.01342. Okay? Using the approximate value. Because I'm setting it up using variables, I have the exact value stored. By the way, you can use on your TI-83 or 84 the STO button to do that, alpha S. So you would do the calculation, you would do store, which looks like an arrow. It's down on the bottom left of the keyboard on your keypad on your calculator, and then you would type capital S, alpha S, right? And that stores that, and then you can use alpha S for the value. It's really kind of a cool trick. You can do it in Desmos, you can do it on your TI-83 or 84. All right, so anyway, so now we want our normal distribution. In Desmos, it looks like this, normal distribution, okay? And we need a mean and a standard deviation. I'm going to do the mean M and the standard deviation S, okay? I'm going to click the hourglass here to see the distribution. You can notice that the peak occurs at 0.1. That's the mean. Standard deviation is about 0.013. 0.013 encompasses about 68% of the distribution to the left and the right. Okay, and we're interested in this particular case, the probability that p hat is below. So we take one particular sample. What is the probability that p hat? What is the probability that p hat, the ratio of wins to total, is less than 0.12? Right? Now the mean is 0.1, so this is above the mean. So this is going to be a rather large percentage. Okay. What is the probability that p hat is less than 0.12? And so on Desmos, I'm going to simply find the cumulative probability and put in a max of 0.12. On your TI-84 or 83, you would do this. You would do norm CDF. That's under your distributions menu. Your lower bound needs to be negative infinity, so maybe negative 9999, just a really large negative number. And then the 0.12 upper bound. The mean in this case is 0.1, and the standard deviation, you could do the whole calculation here in it, or you can just enter the value 0.01342. Okay, and we get 0.93198, so 0.9320. 0.9320, or 93.20%. Okay, so 93.20% of the time we estimate we're going to get a ratio of wins to total that is less than 0.12. Okay, all right. And so that's using a normal distribution with the ratio 0.1. Now what we're asked to do is now approximate the sum of this series. Instead of p hat, we're going to do x. We're going to do the sum, right? Okay, and so we need to scale all of this up, right? The mean now is going to be, we're going to total all the wins. Not find the ratio of wins to total. We're going to total all the wins. So if we win 0.1% or 0.1 or 10% of the time out of 500 tries, we would win 50 times. Okay? So the mean now is 50. You're just going to scale up the same, it's the same distribution, it's just everything's scaled up by a factor of 500. The standard deviation works the same way. The standard deviation is if you want, I'm going to do this here. I'm going to multiply the standard deviation formula by n, PQ divided by n, right? It's just the old standard deviation multiplied by 500. And I just want to demonstrate how that formula comes out. I can square root n squared. I can square and square root at the same time. So n squared square root, that's n. PQ divided by n. And just to demonstrate how this works, you can combine multiplied square root, n squared PQ divided by n in the square root, simplify, the square root of n PQ. And that's why the formula looks like it does. When you find the standard deviation of the sum of the wins instead of the ratio of the wins, this is what the formula looks like. And it's just the original formula multiplied by n, or in this case 500. Okay, so n 500, p 0.1, q 0.9. P and q always add to 1. Right, and we're going to get approximately, and I'm going to bring up Desmos here again, and m is now 0.1 times 500. Okay, and I could do it this way. I could put 500 out front because I know it's just multiplied by 500, or I could change the formula to what I've got here and just multiply by 500 inside. Okay. Either way, we get 6.708. 6.708. 6.708. It's just 500 times more for the standard deviation. We're just scaling it up to match the total instead of the ratio, which is when you take the total and divide by the number possible. All right. So here we go. Let's go ahead and do this just like this. Oh, and we also need to scale up our p hat value of 0.2, and I'm going to call it x bar instead because it's the mean, or x. Just going to call it x. What is the probability that x is less than? And I need to change 0.12 to, I need to scale it up. So 0.12 times 500. All right. 0.12 times 500 is 60. So what is the probability that x is less than 60? Okay. And it's no longer a ratio, it's a sum or a total, right, of all the wins. What is the probability that the total of wins in a given sample of 500 is less than 60? Okay, and I want to run this just like this here without any correction. Okay, but I want you to notice here that the scale is changed, so we got to recenter our picture, and notice now the mean is 50 and the standard deviation is about 7, right? 7 to the right, 7 to the left encompasses 68%, right? And instead of a max of 0.12 now, we're going to put in a max of 60. And I want to show you that this is the same, 0.93198, 0.9320. Remember, we got 0.9320. We haven't changed anything. All we've done is scaled up everything. We scaled up the mean by multiplying by 500. We scaled up the standard deviation by multiplying by 500. We scaled up the p-hat value by multiplying it by 500. And so we've scaled up and we have the same value. The reason we do this is now I can make an adjustment. Remember that a binomial distribution is discrete. That may require a little bit of explanation. You can only get whole number values. You can get 59 out of 500, and you can get 60 out of 500, but you can't get 59.3 out of 500, right? When you're adding up whole numbers, you're always going to get integer answers, and that's called discrete. A normal distribution is continuous, and it includes decimals, and so that's why the normal distribution does not truly represent precisely the binomial distribution, but it's a method for approximating. And so what we want to do is we want to estimate a little lower, because we don't want to include 60, because to be less than 60 means we have to be 59 or less, right? So what I'm going to do is instead of 60, I'm going to do 59.5. 59.5. That's called a continuity correction, right? And here's what we do here with our calculator here. Norm CDF. We're going to do some really big negative number, negative 9999, all the way to 59.5, with a mean of 50 and a standard deviation of 6.708. Okay, and that's approximately, let's go ahead and do this, 59.5, 0.9216, 0.9216, 0.9216, or 92.16%. So it's a little bit less than without the correction, right? Hopefully more closely representing the actual value, right? And then we can approximate this with a totally different distribution, a binomial distribution, using your binomial distribution feature on your calculator here. And I'm going to leave in Desmos, I'm going to leave the distribution, the normal distribution up here, because I want you to see them superimposed on each other. All right, but a binomial distribution, there we go. And trials are 500, and the probability of success is 0.1. Notice how closely they match. There's a little bit of a fudge factor actually, but they match really closely. And that's because the peak actually occurs, if you look at it, between 50 and 49, which is kind of interesting as well. All right. And we want to do a binomial CDF. That's going to be one of your distributions. And I'm not sure exactly what the wording is on your calculator. Look on your distribution menu. Binom CDF, and I'm not sure about the entries here. I do know you need the just like I did here, you need n, you need the 500, you need the 0.1 probability, and then you need the lower bound. Actually, I think it's just the upper bound, in this case 59, right? Because 59 is the first whole number that's less than 60. Okay, So let's go ahead and find the cumulative probability all the way up to 59, right? And notice how this works. We've got discrete bars instead, right? Not continuous area. This is what's actually happening in this situation. And the shaded area covers all the bars, right? If we went up to 60, we'd cover a little bit too much. So we had the adjustment to bring it down. We didn't actually bring it down enough, though, because our total cumulative probability is 0.9190. 0.9190. So even a little bit less, 91.90%. Okay? And so these are three distributions that approximate the same thing, really. That's kind of what makes this confusing. Three different ways. So there's formulas here for the ratio of p hat. The standard deviation is the square root of pq divided by n, where q is 1 minus p, right? And if we want to scale it up and approximate the sum total instead of the ratio, the formula is the square root of npq, right? And the mean of the standard of the p hat proportion is 0.1, whereas the mean of I should indicate it here is NP for the total, for the sum of the count instead of the ratio, right? And then we can adjust by a factor, by a half, to move it left and right a little bit, depending on whether we're doing a less than or a greater than situation, right? And then we can approximate using the binomial distribution on your calculator as well, which uses much more complicated mathematics behind it to calculate the exact answer. All right, so hopefully that helps. Don't hesitate to book a live lesson.